Thank you. So hi everyone, welcome. Thanks for joining. I'm going to be talking about a stochastic second order method today that basically builds up on a second order method called cubic regularization of Newton's method that has very nice convergence properties. So let's dive right in. We have the typical finite sum structured objective functions that are unconstrained, continuous, and we assume second order Lipschitz continuity, even though we really need the explicit Lipschitz constant. And specifically, we assume non-convex functions. In this setting, the best that you can hope for based on second order methods is finding a second order critical point or a local minimum, which is the case where you have so-called strict saddle functions that when the gradient vanishes and the Hessian is positive semi-definite, then you're guaranteed to have a local minimizer. And there was an interesting talk, I think, yesterday on low-rank problems where you have the same property and you can also show that local minimizers are actually global. Yeah, right into it. So why do we even want to use second order information? We think that gradient descent has two common drawbacks. The first one, you probably all know, the zigzagging effect, which basically comes from a local convergence rate that's depending on the problem conditioning. And the second one is that the global convergence rate of gradient descent is pretty slow. One thing that can happen is that around saddle points, which you can see here, first order methods like gradient descent in green or stochastic gradient descent in purple may take very, very small steps, which slows down the progress. While when you have second order information, the steps stay sufficiently long. You can see the Newton method here, and our method is the blue stars finding the local minimizer quickly. Just an overview. For the standard methods, gradient descent and Newton, you have a linear and superlinear quadratic, superlinear local convergence rate. And what we have here is the so-called worst case complexity, so the maximum number of iterations you might have to take to find an epsilon critical point. That's this row here. On top, you always have the per iteration complexity. So in gradient descent, that's just n times d. And on the bottom, that's the number of iterations. What's interesting here is that Newton and gradient descent may be both, and in other words, Newton may be as slow as gradient descent from a global perspective. And there's this other method, the cubic regularization, which is actually an extension of trust region methods that has this epsilon to the power of 3 over 2 worst case complexity. And this has been shown to be optimal for second order methods. But it has nd squared per iteration cost. And what we set out to do is d squared, that's allowed, but also n might be too much for some problems when you have really large scales. So we set out to reduce this to, let's say, the average of the sample size that we use. And in the same session here, there's going to be a talk later. I called this accelerated gradient descent plus negative curvature descent. Correct me if it's not right. But I think it's somewhere in between the arc 3 to the power of 3 over 2 and the Newton gradient descending. But it has significantly lower per iteration cost. So just to introduce the framework, the Newton step itself can be viewed as minimizing a quadratic model at each iterate where you are, or stepping to the critical point of the quadratic model. This step cannot be defined at times when the Hessian is singular, or it can be even ascending, which is what we normally don't want when minimizing a function. The problem here is if you have a if you have a function that you want to optimize and you're at a certain iterate right now, this is the small x here. This is the same function in both plots. And you do a quadratic model, what you assume is that the curvature stays constant. So the quadratic model is this blue mesh grid here. And Newton's step would actually aim at this little triangle. But if you take this step, you end up here, which is ascending. And the point is that along this axis, you have an order 4 polynomial. So you underestimate the change in curvature. What happens in trust region is you say, okay, we cannot trust the model too far away from the current iterate, so we're going to restrict this optimization problem of minimizing the model to a ball, depending on the norm that you take, around your current iterate. So here would be trust region steps for different sizes of the trust region. Mathematically, it looks like this. You have the same model, and you constrain the step that you take to a certain step norm, which is this trust region radius here. And then afterwards, you can also assess the step. You compute this ratio, which is essentially the function decrease over the model decrease, and you only accept this step if it's, let's say, 20% of the model decrease. And then depending on this ratio, you can also enlarge your trust region to allow for larger steps in the next iteration. Another thing that you can do instead of constraining the problem is putting a penalty on the step size norm into the objective function. Actually, the trust region approach is equivalent to a quadratic penalty, but what you can also do, and this dates back to a method proposed by Nesterov 2006, is to do a cubic penalty term. And the one that we build up on is from Carty, Strand, and Go 2011. And then instead of having a trust region radius that you actually update this penalty parameter sigma k, that's a penalty on a step size. What this method does is it has a global second order convergence guarantee, it has quadratic local convergence guarantee, and you get this optimal worst case bound of power O of epsilon to the power of -3 over 2. It allows for a Hessian approximation. It needs sufficiently good Hessian approximations, which the equation will be shown in a minute. And it also allows for the models that we solve on the way to be solved approximately. But the point is that so far there was no such Hessian approximation known, and specifically quasi-Newton methods do not satisfy this agreement condition. And also you need full gradient information, and together you have an iteration complexity depending on n. And that's where our contribution comes in. So we showed that by subsampling the Hessian, in case of the sum structured objective, you can actually find such a BK in every iteration, and we extend the framework to stochastic gradients, which has been done in parallel by Cartes and Scheinberg, and they arrive at the same result. Thus, we reduce the iteration cost, and what we also do is we have a Python implementation of the cubic regularization method. So before it was only in Fortran, and now you can access it via our GitHub in Python. That's our algorithm. It's basically exactly the same as the original ARC algorithm, just that in line 4, in each iteration, we sample the gradient and Hessian information. Then we build this cubic model, you solve it, you assess the step by how good it is, and then either accept it or reject it, and update the penalty on the step size norm. The agreement conditions that we have, the first one is from the Cartes paper. You can kind of intuitively interpret it as that the Hessian approximation and the Hessian itself, they need to be consistent along the path of SK, so the steps that you take. And another thing to note here is that as the algorithm converges, the steps are going to converge to 0. So the more progress we make, the more accurate Hessian information we actually need. And the second one, that's the condition that we came up with, is a similar one for the gradient case. The Hessian sampling, I'll present this one, but the gradient one works basically the same. You don't need unbiasedness for our framework, so you could do importance sampling or whatever you want here. You just average the individual Hessians out, and then we use a concentration inequality called Bernstein's inequality that says that with high probability, the error that we make is going to be in this range here. And now if I use this term on the left-hand side and plug it into the agreement condition that I've just shown, and then you rearrange for the sample size, which is down here, you get this theorem which says, okay, if in each iteration you sample such that this holds, then your Hessian approximations are good enough, let's say. And what you see is, okay, so kappa g here, that's the Lipschitz constant of the gradients, and d, that's the dimensionality, so the higher these terms, the more you need. And also, again, as s goes to 0, as we converge, you will need more and more data points, and eventually, like the last iterations, might actually need a full set of data points. I benchmarked this to some other routines that you could come up with, like just linearly increasing the sample size or exponentially increasing it. So ours, that's the dashed black line, and the one that comes closest is the exponential. On the left, that's the performance, and on the right, that's the sample size on a data set called COF type, and we do a logistic regression there. And in this case, our sampling looks pretty much like the exponential one. It doesn't need to be. Sometimes it also goes up and down. And the performance is also comparable, but what's really nice is that you don't need to tune any parameters. So for the exponential one, I had to know more or less how many iterations it was going to take. And our method just does everything automatically. Yes, then the subproblem minimization. That's where the most computational work comes into play. The point is that each of these cubic models has a local minimizer and a global minimizer, and you want to find the global ones. And also you get saddle points and actually a maximizer. Finding the exact maximizer is pretty expensive, so it's usually not affordable. What we use is a so-called Lanczos process that builds up a Krylov subspace, and we minimize the problem in this Krylov subspace, which can be done cheaply because then the problem has a tridiagonal structure. And the point is that, so you build up these subspaces, and the worst case that can happen is that you do this d times. And that's where the O of d squared comes from our per iteration cost. It might be less than d, thanks. It's often less than d in the first iterations, but it's in the worst case, it's d squared. And actually, the convergence of this Krylov subspace process is not yet well understood. So that's an interesting point for future research as well. Yes, experimental results. We tried a logistic regression, but specifically added a non-convex regularizer to add saddle points and stuff. The first one is where n is far bigger than d, and d is fairly small. So here this is cuff type and Higgs, two common libSVM data sets, and we benchmarked all kinds of methods. So the dashed black line, that's our method. The red and black ones, that's arc and trust region. And then on top, so here I have LBFGS, Saga, SGD, and BFGS. And this is over time log suboptimality. And you can see that the first order methods, for these small dimensional problems, they take way longer actually to optimize. And then we have a multinomial regression on the CIFAR data set where D is fairly bigger. But also in this case, you can see that you progress quickly with, for example, SGD here, but then the second order methods all overtake after a couple of seconds, let's say. That's the same data set over time on the left-hand side and over epochs on the right-hand side. Yeah, conclusion and outlook. As I said, we reduced the iterational complexity from nd squared to average sample size d squared. We think that this is the first subsample Newton method that has a quadratic local convergence. It's one of the first that actually stochastic trust region or cubic regularization methods, and it has second order guarantees. What would be a nice further step would be to apply this in training deep networks. There's been a nice presentation yesterday, but also there's this paper by James Martin. It's already 7 years old, but which they do something very, very similar, and they get very good results on, I think, a deep autoencoder. And then the subproblem minimization, as I said, in the worst case, it's d squared, so it would be cool to get this down to a linear time in d, either by understanding better the Krylov process or by using other methods, and there's a lot of work going on here too. And then, of course, as I said, you don't need an unbiased estimator, so you could do important sampling there. That's already it. Thank you very much for your attention. And here's our GitHub link. If you want to check out our implementation, feel free to play around and give us feedback. I'm looking forward to hearing your thoughts.
Thanks very much for your talk. You had a slide on the sample size that you're using.
Yeah.
Could you give us some additional information for your sample size scheme that you're using, because those are only bounds, right? Where you have to stick, like you have to stick within those bounds, but like how do you sample exactly?
So, so you know D. Delta, that's a probability that you want to have. Actually, I think I have this in the backup slides. We say it should hold with probability 1 minus 1 over d. So that's it. That's the practical implementation. And then instead of, so if you don't have the Lipschitz constant of the gradient, you can just use some constant actually. And the big drawback with this method is that you don't know SK before you actually sample. But that's not actually, so that's born from the original agreement condition by Kartis et al., where you also have SK before you actually know how to approximate the Hessian. So that's the main drawback of this method. What we use is just SK minus 1 and say, okay, it's roughly continuous, so the step size is going to be fine. You could also sample and then check if you actually survive or not. Yeah, but that's the way that we did it, just that there should be SK minus 1.
And
Yeah, sorry, yeah, so, sure. So you round, if it's not an integer, then you round up, but yeah.
I would like to ask, in worst case, how the size of SK compare to N? Like you said, you have some improvement over ND to some SK
Exactly.
commonality of D.
Yeah, you can see this here. This is pretty typical. So here we have 8 iterations, and at the end it's N.
I mean, like theoretically, what's the theoretical?
We don't know. We didn't check. Would be interesting to see how much. Like, you mean the average distance that you can expect?
Average size of SK or SB or something like that.
Yeah. No, we didn't check this, but good point. This would be interesting to see.